Oh, it's good to, yeah, I almost forgot to record, like, you guys can like remind me if like, you can see that like I'm recording, right? If you find that I forget to record, like, let me know. So, so I guess some logistic thing, you guys should realize that we have a homework due this weekend. So you're supposed to submit to Canvas. So, and okay, maybe we will talk a little bit more about that. Like it's basically just a revision of like some probability, basic probability. So you can, I guess, I just apply base rule to solve the problem. But I have some extra credit, like just trying to, I mean, give you guys some incentive to write a program to try to compute the probabilities. So it becomes similar to what we did last time, like for the Monty Hall problem. So maybe I guess we'll talk a little bit more during the break. And let's see. And I guess I will share my screen here first. So we kind of talk about the Monty Hall problem. I guess I just kind of make it kind of complete. So yes, someone say something. So I guess I just quickly go through the solution. So I guess the analytical solution. Of course, last time we showed that okay, I can write a program, then we can estimate the probability. So, but if you remember, like we have the problem is like, let me just make it full screen maybe. So I have like 3 doors. So we have a game show here. We have 3 doors. We have a host, and behind one of the door there will be a prize there, maybe a cash prize. Then there's a player that is going to pick a door like initially. After he pick a door, the host will open the other door, like besides one of the other doors, besides the door have the cash prize or the door the player pick. Let's say the host pick this one, then he'll ask the player if he want to switch to the other door that the host didn't open. So if he decided to switch, then he will switch to this one. If he decided to stay, then he will stay for this one. So then the question is like, is it better to stay or is it better to switch? Of course, the probability for staying is quite obvious. If you are staying, then basically you have a cash prize that is randomly kind of selected in one of these 3 doors, and then like the player is also randomly select one of the 3 doors. So therefore, the probability of staying and winning, or I guess I stay and win, is just 1/3, right? This is quite clear. Now the tricky question that stumble like many people, including the famous adults, is that like intuitively many people think that it doesn't help to switch, but actually we can if we kind of like think of this like step by step, is not that difficult. So let's say like with the loss of generality, let's say the player just picked the first door. So the player just picked the first door, like say, and then like that's basically 3 cases, right? So 3 cases have equal probability. So the first case is like the cash prize is like at door 1, I don't even know how to spell cash, at 1. So for this case here, then the host will pick either this door or this door. It will either reveal this door or this door. So let's say the host pick this one. But in either case, if you decide to switch, you will switch to the door that you originally picked the correct one. Now you will switch to the wrong one. So therefore, the probability of winning, given that like, okay, of course, like for all these cases, maybe I don't even need to write conditional. All these cases here is assuming, okay, here like I'm assume switching to the new door. Then in this case, for case 1, if the cache is behind door 1, then the probability of winning is just 0, right? So apparently it's just 0. Now, if like for the second case, let's say the cache price is here. Then the host, okay, then the host actually can only pick one door. It's basically can only pick this one because the player picked this one, and the cache is here. Then the host can only pick this one. Then therefore, if it switch, if the player decided to switch, it will pick the correct door always. So therefore, like for this case, I cache at 2 here. The probability of winning is always 1. And similarly, for the third case, if I am here, if the cache price is at here, the host will pick this one. And then if the player decide to switch, will pick the white door again. I pick the third door. Again, the probability of winning is 1 as well. So then, of course, like for all these 3 cases, the probability is the same. It's all 1/3. So therefore, like the probability of winning is 2/3 given switching. So that's for the Monty Hall problem. I didn't even write down the problem. Monty Hall. Yeah. So I guess there's no question here. It's like okay. Let me look at the let me look at our numerical solution again. Like we have trying to compute the probability using some program, right? Because after all, the title of this course includes probabilistic programming. So I didn't use any package, but I just use NumPy here, right? So, but I want to emphasize here what we are doing here precisely. What we are doing here is actually I just literally repeating the experiment like 10,000 times. So basically, I just have 10,000 times randomly have a price randomly put in one of the 3 doors, and then randomly have the player pick one of the door, and then like according to the rule of the host like pick the door, and then like I let the player either switch or not switch. And then I just count like how many times winning and how many times losing. And then like I estimate the probability using the count, like basically the count. If I swap, let's say if I swap, then I count like how many times I actually win over the total number of times that I did the experiment, right? And this estimate me the basically the probability of winning given swapping. So far so good. And actually this looks very much intuitive, right? But I want to use this as a motivation to kind of mention something that you probably, okay, yeah, I will use my tab instead. That's a little bit easier to, let's see. How do I move this to? Okay, yeah, okay. So yeah, actually I can move this, then I can see your list and I can see your, let me know if you have any questions or so on. So let's see. So the first thing I'd like to talk about, by the way, like it's probably is good to, okay, maybe later on. You see, like when I did this experiment, like what we are doing is basically using an assumption that people actually learn that. Okay, why I cannot write? Let's see. Oh, there's some problem with my. Oh, yes, I need to. Let's see. Just wait a second. I'm sorry about that. Let's see. Here. Now I can write. I don't know why. So So the first thing I want to talk, okay, the first thing I want to really talk about like today is the law of large number. So you see in the example we have like trying to solve the Monty Hall problem is actually one of the example using law of large number, and we didn't realize that. So basically the law of large number is saying something like that. If we have some I have a probability distribution. Let's say I have some px here. So I sample it many times. So I sample, let's say, x1, x2, and to xn. Let's say I sample it n times, and then I'm sample the same distribution, and I sample it randomly. I'm not random, sample them independently. So therefore, sometimes people call this like IID, like identically and independently distributed. And now let's say like all these are realization from this random variable, right? I just sample it n times. So if I have a function of this x, let's say I have fx, basically I have x mapped to fx. So I have like fx1 and fx2 and so on and so forth up to fxn. Now if I going to compute the average of this fx1 up to fxn here, so I have just basically doing like fxi I equal to 1 up to n. I take the average of that. So this will basically converge to the expectation of fx as n goes to infinity. And if I want to make it really kind of rigorous, like this is like people will say like this will almost surely converge to the expected values of fx. And okay, AS is like almost surely. So this almost surely meaning that like the probability that 1 over n I equal to 1 to n fxi here is equal to, actually I should write this as big X because it's a randomly sample these things, is equal to expectation fx with probability equal to 1. So this is what we mean by almost surely. And this is actually known as the strong law of large number. And so if you think of like in the Monty Hall example, what we did there is like, each time we sample that, like we can think of the F is what? F is a, let's say if I want to estimate the probability of winning given like swapping, something like that, right? So I have this, the F is basically like, you can think of F is in this case would be like kind of a indicator function that if I win, basically if I win, maybe I use this, yeah, use 1 here. If I win, we will basically like, I have the outcome either winning or losing, right? So if I win, I will have saying that will give me 1. If I have like losing, then I will get it 0. So what we did there is like we are using the law of large number, and we have the fx here. F is now is the indicator function. We're just counting the number of winning and losing, right? And for n is really big, that will basically converge to the expectation of that one. Actually, I writing this is a little bit sloppy here. So maybe let's say let me say the variable is okay. Let me write it like this. Let's say O is the outcome. My outcome will either win or lose. So I will have like outcome will be winning. Like then I will, if my outcome is winning, then like my indicator function, like this is basically the F here earlier, I will be equal to 1. If like it's losing, that will be equal to 0. So this guy like on the right hand side is what we're doing in the experiment. So if we do that, it's basically counting like how many times we win. Right, we just sum all of them together. We'll be just counting how many times we win over the total number of times we do the experiment. And then the left-hand side will be this indicator function. This is again this F here with the random variable is basically this O here. Will be, oh, let's see. Will just give us the probability, right? This will just give us the probability, right? Because like this will be basically, this will be equal to I have like probability. Okay. This will be probability winning. The expectation of this guy will be the probability O is winning times that the indicator function 1 O is equal to win here plus probability O is losing. The indication function O is lose here. And then like this will be just equal to 0, and this is equal to 1 here. That will just give us the probability of winning here. So anyway, like I guess it looks like I'm just making things complicated. And this looks I mean kind of I'm sure like this looks so intuitive that some of you probably think that I'm just saying something like meaningless. But okay. So let me give one more interesting example first, and then I'm going to show the law of large number, but not the strong law of large number. Proving the strong law of large number is quite technical, actually, it turns out. So, we won't do that. We will instead we will show a kind of weak version. That's something known as the weak law of large number. Sometimes they just call it LLN here. So basically the weak law of large number is saying something that like these guys will, the left-hand side, this empirical average here, you converge to this like in probability. So meaning that like the probability that like this sum here will be far away from this, let's say, fx, the expectation. Let's say if bigger than some value, like some epsilon or something, will be converged to 0 or something like it will be like some, yeah, it goes to 0 as n goes to infinity. So, but again, before I show this, I'm just going to give an example, like another use of the law of large number that you may find it more interesting. So let's say, let's talk about gambling. I think like many engineers, like you can think of like either gambling or investment, whatever you're in, okay? If you want to do a euphemism, you say it's investment, but it can be just gambling. Oh, wait a sec. Okay. I just want to make sure I use the same notation as the notes is a bit easier. So let's see what okay. So let's say let's say I start with $1. I have $1, or like you can think of you have $100. It doesn't matter. So that's my net worth. That's all I have. Now I have a game that I can participate infinite number of times. You can think of it like gambling or like maybe lottery or like or like some kind of investment or whatever. And let's say if I can bet on whatever amount I like to bet on. Let's say I can bet on X amount, like maybe X values here, and then like I will get back if I win. Basically, there's two situations here. If I invest like X here, so I will either get back XB, so that's if I win. So B, wait a sec. Okay, actually, I didn't use the same notation of my notes actually. X is not the things I invest. Let's see. Oh, actually it is. Maybe I don't know. Yeah, okay, it is. I'm sorry, I take it back. So let's say if I invest X, so I can, if I win, basically if I win, then I will get back XB, let's say. And if I lose, if I lost, then of course I will get back nothing. So that's basically how the game works. Now, so let's say the probability of winning is P, and probability of losing is 1 minus P, right? Wait. Oh, yes, that's right. So so then let's say like if I of course like I should have like let's say XB if let's say okay, let me think of this way. So I have like, let's say I have $1 again like at the beginning. If I invest X, so then like I have like 1 minus X is like not investing anything, right? So then like after after the, so I have x is, okay, x inverse, 1 minus x not inverse. So then after the game, if I win, so again, if I win here, then I should get back how many? I should get back 1 minus x plus xb, right? So let's see, I just want to make sure. No, actually, okay, I'm sorry, like I make you guys so confused here. Because I want to stick with like the whatever written in the notes. So let me don't use this. So let me just, okay, scratch all this now. So anyway, if I win, so the winning probability like is I will use P here, and losing probability I will use 1 minus P here, and I'm going to invest X here. So, and like if I win, I will get back like 1 plus XB. So let's stick with that. So, and if I lose, then I will get back 1 minus X. Okay, I see like why is there's another problem. Like I see this B here. I'm sorry, like that. Okay, okay, this time is okay. So why this? Yeah, that's the problem. Like I'm so sure that I know what's going on, that I didn't read this thing like before I come to class. That's the problem. Let's see. Say, I guess I may better just it's my net worth. If I win, I probably P.
Dr. Chang?
Yes.
What is B in here?
You mean B or P?
The B. B.
Yes. B is like this is the let odd. So I get back XP. Okay, get back XP is okay. So if I have P, then I will get back XP. That, yeah, that seems right. Then if I lose, then like I'll get like 1 minus. Yeah, that's yeah. I make a typo here because I follow in my notes here, and I have a typo in my notes. Then I okay, yeah, that's yeah. Okay, yeah, that's okay. That's basically. I'm so sorry about that. Let me repeat again. So I have X here anyway. Like I have like $1. I have X. I'm going to invest. Now the offset is basically like if I win, I will get back like XB. So B is basically bigger than 1. Otherwise, it is meaningless to invest, right? And the probability for that is like 1 plus XB. And if I lose, basically, like I will have like 1 minus X. And so the question here is like, what should we do? Like, of course, like if first thing first, like if my let's see, look at the expectation first. Like if I am trying, let's say like if I invest, like what is my, how much do I gain or how much do I lose next time? So let's look at the expectation. What do we have next time? So I will have basically my expectation of, let's say, net worth after this investment here will be equal to, I have 1 minus XP with probability P, right? And then I will have like 1 minus X with probability 1 minus P, right? Now, if I have So okay, I guess I would let you think about that first. So what should you do? Like, should you of course, if my bet is too, what I want to say, if my leg odds, if my probability of winning is small, too small, then like it won't worth betting, right? For example, like if my P, let's see, if my PB is less than 1, does it make sense that PB less than 1? Or something like related to that, like if my P is too small and my B is kind of too small, then like it doesn't worth to invest any money on that, right? But let's say if my P is sufficiently big and B is sufficiently big, so what should you do? Like should you do all in, or like should you maybe, okay, let me give you a quiz first. Like, okay, it's better to think about that like together instead of like, so okay, I sorry, I stumbled quite a bit like at the beginning, but do I make my this whole problem like set up like clear? So basically like I have two, basically I have some money you can think of, like I start with just $1 here. And I'm going to invest this amount, like I will have X will be less than either like I can invest nothing or like you can invest everything, I can all in. And basically the game is like that, like I will have whatever like this kind of game, like I have a probability P of winning. And if I win that, I will get back like, of course, since I invest X, right, I will have something more than X, I will get back XB here. And so my, yeah, and my total amount I will get back like 1 plus XB here, say. So, but on the other hand, if I lost here, I will have the X dollars that I invest will be gone completely. I will only have 1 minus X left. Now, I guess there's several questions here. It's like the first thing, like when I should not invest at all. And the second question is like, if it's worth investing, should I go all in? Okay, how about that? Like, I give you five minutes to think about it again. Like, so okay, I'm sorry, like about the earlier kind of like stumbling, but did I make myself clear about like the setup and the questions? Okay, let me repeat one more time. So this is a gambling, a game, or like investment, whatever you call it. Just call it a game. So like you play a game with someone, but this game like is a repeated game. You can repeat it many times. So like many times. Now, and let's say I just make it simple. Like you start with $1. This is your net worth. Like you have $1 to start with. And now like you can invest any amount you want, or like you can bet on any amount like for the game. So like you can either win or lose in that game. Like you have probability P of winning that, or so therefore you have 1 minus P of losing that. Of course, like therefore P is like between 0 and 1, right? And like if you win, basically you will get back like 1 plus XB. So if you invest more, like you get more back. I mean more amount back. If you don't invest anything, of course, like you don't have, like basically if your investment is 0, then like you just get back, no matter what all you have, like you just get back $1 here. But if you have like invest more, then you potentially you can get more back. And of course, like if this, they call this let odd here. If B is bigger, then like if B is much bigger, then basically the let odd is like you expect B should be bigger than 0. If it's less than 0, then of course like, it would be pretty bad. It doesn't worth it. But it also should depend on P, right? Because like, even though like your let off is bigger than 0, if your P is pretty small, then it may not worth to invest on that, right? And if you lose, basically, if you bet on this time, if you lose, then all you invested, like the X dollars, you will get, you don't get anything back. So what you remain behind will be just 1 minus X here. Oops, suddenly I cannot write again. Okay. Yeah, okay. Now then, maybe you can ignore this one. Yeah, you don't need to worry about this. Now then, the question is like, what combination of P and B will be reasonable? Like intuitively, like I should have P and B should be reasonably big, right? So if it's too small, at least I need to know. At least I can for sure that P should be bigger than 0. If B is bigger than 0. If B is less than 0, then it won't worth to invest at all. Right? So you cannot just, even you lose, I mean, even you win, you can't lose money. Then doesn't make sense, right? But even that like B is like maybe big enough. If your P is really small, there may be chance that like it's still not worth playing this game, right? Now the second question is like, if this is worth playing, if this game is worth playing, I mean, remember that this is a repeated game. Yeah, you guys can discuss and think about it. Yes, but is it clear? The setup is that clear? Now as I said, like this is a repeated game. Let me say, emphasize again. This is a repeated game, so it's not like you can only play it one time. You can play it infinitely number of times. So think of like playing stock. Maybe like you can just buying Bitcoin like every day. I don't know. Of course, it doesn't make sense. Like every time I have the same odd here, but something like that you can invest in like repeatedly, like many times. Now the second question is like, if this game is worth playing, should I go all in? All in meaning that like the first time I would just invest my entire net worth into. Yeah, Farouk have some suggestion. Like, yeah, you guys can think about that also. Like, I'll give you some time, 5-10 minutes to think about that. But I guess like the problem setup is clear, right?
Dr. Cheng?
Yes.
I was doing the maths, so I didn't notice when you cut out the equation. Is that equation not valid? The net net.
I guess it's better I cross it out. It may even mislead you guys to. It's not invalid, but it may not lead you. It probably won't lead you to the best solution. So anyone should write some answer here. It's like part of the quiz. As you guys know, this is some of these extra credits. You get some points. Even you don't have a correct answer. But of course, I will give you some time, so maybe 5-10 minutes to think about that.
Dr. Chen.
Yes.
So if probability of win is B, then I get 1 plus XB. But if I lose, then then it is not 1 minus XB. It should be XB. Is it
Yeah. Yeah.
intensity?
That's. Yes, you're right. That's the problem. I was stumble a little bit. I look at it. This is how people define this kind of let-off thing. Like you can think of like this. I mean, like, of course, you can think of like you get back like x maybe w or something. Then what you get is a 1 minus x plus xw, right? So it just combine this w and minus 1 together. So it's like actually 1 plus x w minus 1, and this w minus 1 is b here. So that like in people like to do gambling or investment, they call this a let odd. So I was kind of confused a little bit because I'm actually thinking along the same line as you. So I'm thinking like, okay, I have x there, so I will get back like xw or something like that. But then I look at the notation here. Oops, it doesn't match up. Yeah, so you're right. So but note that it doesn't matter. Just the definition make it this way. So in this case, so therefore B should always be bigger than 0, right? So if B is less than 0, it doesn't. I mean, like yeah, even you win, you don't get anything. I mean, yeah. Yes. So, so did I answer your question?
Yes, Professor.
Okay. Well, actually, for the first question, you can go along like what I erase here. think of like what's the expected value if you invest, like what is the expected value next time? But the second question is more tricky, I think. And I was totally wrong like, when I first came across this problem. It's not actually. It will. You guys like should think about like B and P should be related. Like it won't be like just like P is bigger than 0.5 or something. It'll be like the answer because like it depends on P as well, right? I mean B and P. For example, like if I have for some B here, maybe it's like 0.1 here. You have some P, maybe like 0.5 is good, but then like if you increase your B, like make a bigger odd here. So apparently I should reduce my P, I still like it's worth investment, right? Investing, right? So these two numbers should be related to one another in terms of like whether you want to, whether it's in, whether it's like worth to play this game or not.
Dr. Cheng, doesn't B mean the profit that we will be making on our investment, and P is the probability of winning?
P is the probability of winning, and yeah, P is probability of winning, and B know that it's like this is what we get back. Like again, I just look at this one, like this inside this rectangle here, describe the entire game. Again, like basically you are putting X amount of dollars inside, right? So then like if with probability P, you will get that 1 plus X times B. And then with probability 1 minus P, you'll just get that 1 minus X. So therefore, like if your B is bigger, then of course like, it doesn't matter if your P is smaller, still it probably is worth playing this game, right? But if like this B is small, then maybe I need to have like much bigger P to make this worth playing. Okay, I guess maybe even this is misleading. I just keep let me show this line again. So let's see. Yes, for Mookie, yes, like if, but what's the amount, what's the relationship of B and P to make them? For Vishnu, like I think you have a mistake here. Like you have one away. Why you get like X minus P? I don't think like you will get something like that. Maybe you have a bug when you do the calculation. So so what I'm writing here is not the just will be able to answer the first question, but maybe I will just give you some hint again. So think of like if I okay, what will be the amount that you get, expected amount you get like after playing one game. So the amount will be just like P 1 plus XB plus 1 minus P 1 minus XY. So you do some algebra, then what do you get? Like I guess I will just leave you. Yes, let's see if we'll have something. So can you are you sure? I think you can simplify further or something like that maybe. Let's see. Or maybe you're right. Let's see. So anyone want to? So anyone here that didn't put out an answer, please put out an answer. Then like let me at least get over with the first question here. Like if I okay, let's say like if this is the amount as I said, this is amount that expected amount I will get back after playing this game, right? So then this is what this is like p plus xbp plus 1 minus p minus 1 minus px. Let's see. Then I have p got cancelled here, right? And I have basically I have this is I have a 1 here, I have 1 here, 1 plus what? X bp minus 1 minus p, right? That's what I get. Did you guys get the same thing, right? Let me see. I think like you want to group the x together. This is the things you're interested because okay, think of like x is like you can vary, right? You can vary whatever x you have. Now this is like what you get after basically just playing one time. If this thing is positive, then I will have my next the expected amount, expected return will be bigger than 1, right? Bigger than my original, right? So, but if this thing is negative, then my expected amount will be kind of like equal to, okay, will be negative. So therefore, like I don't worth like investing, right? So therefore, like the question, for the answer for the first question would be like, I would like this guy is bigger than 0. So I don't know how many of you get it correctly. So I'll come back to look at that. So, but are you guys clear? So it's not like you have some fixed P or B, like that will be a relationship. Like you can see like BP is something like you can think of BP as a something like what you some kind of like value that BP will be bigger. Okay, or like I should say like if the kind of some kind of like proportional to the last sum you will get back, and 1 minus p is like when you win, and this is 1 minus p is like okay, it's hard to say like that, but anyway, like this I basically this guy again, like if this guy is bigger than 0, then like I will be worth like playing this game. So you guys are all okay with this answer for the first one? Yeah. Yes.
I was thinking that because if this BP minus 1 minus p is greater than 0
yes.
or equal to 0, for example, if it's equal to 0, then our answer will be 1, right? The expected value is 1. And then the maximum value of x is also 1. This means that we are thinking that we are going all in.
That's not finished. That's for the second question. This actually what I've written down why I cross it out afterward, because what right down here is kind of misleading, but it's able to answer the first question, but it's not able to answer the second question.
Yes, because if we think that, then we are considering that we have invested all x equal to 1.
Yes, if I just look at this one here, it looks like that, like whenever this is bigger than 0, I should always invest all in, right?
Yes.
From here. So if it's something like either if like this is less than 1, then I should do anything. I mean, so not that less than 0, then I should not invest at all. But if it's bigger than 0, I should just go all in.
Yes,
that's why that I don't want to write it down like at the beginning, but
okay, but
yeah,
clear now. The first question is clear.
Yeah, the first question, but this is able to answer the first question. Now the second question. Note that the difference is like this is allow you to do repeated game, right? This is a game that you can do it repeatedly. So let me again give you guys some hints, and then maybe like you guys try to find the solution yourself, maybe. So note that if I'm able to pay repeatedly, so instead of like think of x, okay, yeah, instead of think of x as the actual amount, think of x as just a portion of the money that you are going to involve, to invest in the game. So for example, like if next time like you get $2, then the actual amount you're going to invest will be 2x, let's say something like that. If you have now the net worth is like it's like $10, then basically you invest 10x, something like that. So now x is not the actual amount, but it's just the ratio of money you're going to invest on that. Now think of like instead of white, so think of now also like let's see, what should I think of? Let me introduce a new random variable. I call it z here. Let me call it z here. Z can be either like 1 or 0. Let's say 1 is correspond to winning, and 0 is correspond to losing, let's say. And I have something like if let's say if I just look at like I pay a couple of times, maybe I pay two. Maybe I need some space here. Maybe I keep this thing but erase. Okay, is that possible to move? Maybe I write this thing in a corner. So again, like I win with probability P. So I will get back 1 plus XB here. If I lose, I will have probability 1 minus P. I will get like 1 minus X here. So again, I have this C, which is indicating whether I'm winning or losing. So let's say if I have like several cases, let's say I pay it 2 times. So I have like either C, I have this C sample 2 times to get like, let's say, if I have win-win. So if I win-win, then what do I get? I will get like, first I invest like 1 plus, I will get both times I win, right? So I will get like 1 plus XB. And then I will get, I win again. So I have 1 times XB squared. So this is like the situation. If I win-win, I will get this amount back. So again, like X is a ratio of current net worth invest on the game. So if I have, let me give some more example. Like if I have, turns out it's win-lose, then what will I get? I will get like 1 plus XB times, first time I win, I will get back 1 plus XB, right? Then I pay again. Next time I lose, I will just have my net worth shrink by a fraction 1 minus X, right? So we will be just multiplied by this 1 minus X here. And let's say like if I pay like more than 2 times, maybe I can pay like 5 times. I have like win, lose, lose, let's say. Then what do I get? I get like 1 plus XB square and 1 minus X cubed, right? So, okay, is that clear for the moment?
Professor Chang?
Yes.
So I don't understand why when double wind, we got 1 plus XB square. Because first we start with $1, and then price is XB. And then another win got another price XB. Isn't it 1 plus?
Yes, but yes, you're right.
I don't understand. I'm sorry.
Yeah, the order is not important because I can write like this. Yeah, but then I just group the power together. Yeah. So you answer your question already, I think, yourself. So so any other questions? So basically, you see, like this is just counting, right? So in general, like if I have like pay n times, so if I pay n times, I have like so whatever.
One question.
Yes.
So I wanted to know that in case of a double win, we are just squaring 1 plus xv raised to the power 2. But why aren't we multiplying it with the probability p as well, since the probability might also have some role to play with regards to how we're going to win or lose?
Yes, you're right. Yes, you're right. But here, like, it's coming up because it's exactly like as you said here. The probability will play a role, but play a role at where? It's playable like actually how many of this win and lose you are going to get, right? Because, for example, like if I pay like n times, n is very big, then I will have like approximately np so many times I win and nl or n1 minus p so many times I lose, right? So let's say like for n is very big, so n goes to infinity, let's say. So then I will have like about like np so many times. Yeah, okay, I just repeating what I said, but are you agree with that? Like,
yeah, so
yes.
don't you think we should also multiply it with the p, the number of loses and wins with the respective probabilities that is related to their occurrence?
Oh, let's see, like your voice is a little bit soft. I cannot hear you clearly, actually.
Yeah, so I am saying that in the case of double win, we multiply 1 plus xb with itself, and in case of win lose, we multiply 1 plus xb with 1 minus x. So
yeah,
I think we should also multiply these values with their corresponding probability, since probability might also have some role to play in winning or losing a particular event.
yes, the probability will have some role to play. And the probability, let me finish that, maybe it will be clearer. So for this case, let's say I have n of them, like n is very big. So I will have like about like np, maybe like this n is like 10,000. And then maybe like my p is about like 0.2, let's say, right? Then you with high probability that, okay, I guess abusing a probability. So that like you will have, let's say, about like 2,000 win, right? And then maybe you have about like 8,000 lose. That's you have like 2,000 is basically MP, and you have like 8,000 like and 1 minus p like loose here. So then like what will be your net worth after playing these 10,000 games will be like 1 plus xb times 2,000. That's basically MP, right? And times 1 minus x n minus n times 1 minus p, right? And this is like this p now is inside this expression here. And
just one thing, that what does n represent here?
let's say that again.
What does n represent here?
N is the number of times playing the game.
Okay, sure.
Yeah. Now then, with this, can you try to answer the question again? How if I can pay like infinite amount of time, then let's say this is I call this like WN. Let's say like this will be the net worth after playing this game n times. Then I guess then it's actually you can think of okay. If I want to maximize this net worth, it will be the same as trying to maximize, because like this, actually I can write this as a 1 plus x b to the p, 1 minus x, 1 minus p to the power n, right? So maximize this guy will be the same as maximize this thing here. And it will be the same as like maximizing log of this guy here will be the same as like log, or maybe I just, yeah. Can you guys complete this? Like just what will be the x then? With this, I think will be able to complete the second. So actually, apparently, you see like most likely it should not be going all in, but instead like the question would be like, what is x? How x will be related to like b and p and so on, b and p basically. So are you guys computing that? Like, so is that clear? I think it's a simple algebra, some simple calculus. So you guys are okay, like if you, I'm not sure, like because I have no response, so I'm not sure you guys are doing the computation or like you have any. You guys are done or like, oh. So, okay, are you clear like what I mean, how you can solve this one, the second question here, like, please say yes or something, or like, okay. Oh, okay. So, so I repeat again, okay. Let's see, like, is this one is clear? Like,
Yes.
so for a fixed n, let's say like anyway, like fn go to be very big, this will be approximately. This is actually exactly where the law of large numbers is using. So it was used like implicitly, but basically by law of large number, the net worth will converge to this number here as n goes to infinity. And of course, I can just pull this power n outside. That would be just equal to this, to the power n, right? Now, then therefore, like if this guy is bigger, then like my net worth is bigger. This is basically the weight of like increasing your net worth, right? So therefore, this is like something I like to maximize, right? So of course, you can maximize this thing directly. You want to maximize with respect to x, right? So, but I suggest it's easier. You can maximize log of this product instead. It's typically easier. So we can maximize log of this guy with respect to x. Then we'll give you the optimum x, like what you should invest, right? That's Zoom is very weird. Like you guys are okay, hopefully. Last time I tried to have image, I tried to download it. It didn't. Okay, this time it seems that I'm able to download that. I have something from the here. Yeah. So you want to solve for x, right?
I was thinking about getting the critical values, because on the critical values we will be having the points where we can find a max or a min value. So that's why I put the whole equation equal to 0 and try to solve it.
You okay. I don't think you take the integral. I don't know integral. You didn't take the derivative, right? I think you forget to take the derivative. So you're trying to maximize this guy. So if you go back to like the first class in calculus or something, then you're trying to like take the derivative of this guy with respect to x, and then like just set it to 0, right? Okay. How about I give you like okay. How about like I take this as a break anyway, like so maybe come back 4:30, like so but you guys are clear like what's the question like I'm asking here? Like so for the second one, like I give you a big hint like the solution for this guy. So it seems that like you cannot do basically you shouldn't go all in. So the solution will be like available here. Like actually, I give you the big hint already. Like so, this is just you can finish that by doing calculus. So trying to find the maximum for this expression here with respect to x. So and of course, like this x should depend on b and p. So let me know if you have any question. I will wait until like 4:30, like so I'm around anyway, but like
So now a break time.
yeah, I guess I'll give. Okay, yeah, I have one yeah, I have one answer now. So I don't know because I didn't see like too many answer. I'm not you guys around or like you're stuck or something. So yeah, let's maybe like take a early break here. So then like we and also give you some time to compute that, even though it should be very quick. And then we'll come back to just finish this. Say 4:30.
Okay.
Yeah, I have some more answer now. Okay, I guess we'll continue. So I guess many of you get the correct answer. So that I guess typically, I guess really the crowd intelligence is pretty accurate. So the answer that most of you, the majority got actually is kind of correct. So so maybe I just write a couple lines here. So in case for some of you may not get the answer. So I can take a log of this guy, right? So I'm trying to maximize log of this guy. So I have log 1 plus xb p plus 1 minus p log 1 minus x. So I take a derivative with x here. So I have like p 1 plus xb. So take derivative of log something is 1 over something, right? So take derivative with respect to x inside, I get b back here, and plus like 1 minus p, 1 minus x, and I have minus 1 here. And so this should set to 0. So I don't think I'll go for the algebra, like, so I just write down. So this should give you x is equal to bp minus 1 minus p over p. Actually, this can, if you look at the expression here, you give you kind of like some confidence, right? If you remember the first answer, the solution for the first question, because remember that you should bet only when bp minus 1 minus p is bigger than 0, right? And this is actually, this also reflects that. So if like this is less than 0, you shouldn't, you shouldn't invest, you cannot invest in negative money. So if like this is less than 0, it gives you a solution is negative, apparently something is wrong. This is not actually the maximum. So therefore it's kind of like this result is consistent with the first question here, but only like you also have this denominator here. You have this ratio instead. So it's not that like once you have this bigger than 0, you should invest, you'll be all in, but instead like you should kind of invest on like this ratio here. And apparently like you have this is equal to 1 when p is equal to 1. Right? So if p equal to 1, you just get the numerator is b, and then like you'll be all in. Okay, and so you just look at that. Like actually, it's a good habit like to check your answer. Like just look at several like special cases, and then you can argue yourself that your solution looks right or not. And I guess like one thing I motivate you guys. I think okay, now I can say like what is this, because I don't want to give the name of this thing like so that you can too easily go online to look for that. This is like known as the Kelly's criterion. It's like quite famous in economics or something. Like you see like it would be very useful. For example, like in stock investment, like you have some kind of net worth here, and you know like what's the odd there, then how much ratio of your net worth should invest on something, like should be governed by this Kelly's criteria. And of course, I use this to motivate the law of large number. It's kind of hidden somewhere. The law of large number is used here because the law of large number is saying that. So note that like each of these guys is a random variable, right? So this is each of these things is actually a random variable. You think of that. Of course, this is a product, but if you think of the log of this thing instead, so I have think of like each time you have a gain of net worth is like okay, maybe I write it this way. Basically, I have Wn can be think of like delta Wi product I is equal to 1 to n, let's say. So delta Wi, I'm not sure it's a good notation for that, will be like a gain of, maybe delta is not a very good notation. Let's see, let me think of like a better notation. Maybe I put a ratio inside, like R, like stand for ratio. So each time, like how much you differ, like in terms of like you increase or decrease your net worth, this would be a random number, right? So, and then like, of course, this is a product. I cannot use law of large number, but if I consider like log n here, so I have sum of this I 1 to n, log out I here. I have some of these random variables here. And I know that this will converge to the expectation of this thing. So n expectation, if I don't have over n here, there's n of expectation of I here. So that is essentially what I'm trying to maximize this guy's that we write down earlier. The expression is basically log I here. And so that's the law of large number. And of course, I didn't even show like even the weak law. I said that like this, I have a strong law that almost surely this will converge to this guy. And for weak law, we will converge like proportion, improbability. So I have something like this is the weak law here. So maybe I will just quickly for completeness. You may not see this again, but maybe it's good to see that showing the weak law. So basically, like we'll use this so-called like Chebyshev inequality. I don't know how to spell that, Chebyshev inequality. So the Chebyshev inequality is saying something like that. If you have a random variable with y, let's say y here, the probability of y deviate from the expectation of y. With probability the probability of deviating more than like some constant a will be bounded by the variance of y over a square. And okay, and this in turn I can show that using something called the Markov's inequality. But okay, let's show this later. Okay, I will leave it later. But let's show the weak law of large number using the Chebyshev inequality. Actually, if you look at this, two things is pretty similar already, so it looks like it's pretty easy to show. So let's prove proof of weak LLN using the Chebyshev inequality. So let's see. So what I'm going to do is I want to make this as y, right? I will just think of this thing, this empirical average as a random variable y. Now I want to find the variance of y, right? So what's the variance of y? Oh, actually, I guess this is a good exercise for you guys also. Like I think like it's, and I think you should be able to know that. So like if y is equal to 1 over n fxi I equal to 1 to n. I don't know whether, yeah, maybe it's not worth as an exercise. So variance of y is what? In terms of course, I need to know like what's the variance of this guy. Let's say if I know variance of fxi, and let's say like all of them are ID, so like all of them is just equal to some variance of fx. So what was variance of y?
y minus the mean squared the expectation of that?
Yes. But what's the precise, or like you can start with, maybe I will make something simpler so that like it will be less painful for you guys. So let's say like fx and y are both like zero mean. So let's say I have like y is like both zero means here. Or like actually if I say like fx is zero mean, then like y will be automatically zero mean, right? So, and then like what will be the variance of y? Maybe this is like still worth like for you guys to answer. So this will be like quiz 3 maybe, like maybe I give you like a couple minutes. Like so again, like I have y is equal to the average, empirical average. So I better use the same n here. One of them using uppercase, I should use uppercase here also. So it's like my y is like just I have this some fxi here. You can just maybe call fxi just zi or some random variable. And then I know what's the variance of fci, or like I know like what's variance of fx. So this xi here or iid. So therefore like they have same distribution. Like variance of fxi is just variance of fx. And now the question is again, what's the variance of y? Of course, the variance of y in terms of fx, in terms of this, in terms of maybe I should, what's variance of x in terms of variance. Okay, better improve my handwriting. Terms of variance of fx. So and I know that like I make things simple. I just assume like things are zero mean here. Oh, okay. Like let me just give you one more hint. Remember, like we have last time, like variance of y is something like expectation of x square minus this. We derived this before. Sorry, why I put x here? Sorry, y. So are you guys trying to do that? Like, are you guys trying to
Yes, I am trying to do.
Okay, let me give you 2 minutes then. Like, so. No, that like let me emphasize again, like this guy are IID, so you need this condition here. They are independent, basically, each of these xi. So anyone is like still working on that? You can raise your hand or something. Yeah, I'll wait for you a little bit then. But maybe meanwhile, maybe like I know that like even I give a assumption say make it easy like to have like the mean is equal to 0. Note that like the result here is not affected by whether the mean is 0 or not. So one thing you need to know that like I have like the expectation of y, the mean is the same on the left hand side and right hand side. I have the mean here for the expectation of y is equal to 1 over n. So I have okay, again, remember that expectation is linear. So expectation 1 over n sum over f xi here, right? And I can have this expectation go into each of this term here, each of this term here. So I have expectation fxi here. So, and this expectation fxi is just expectation fxi. And so I will have n of this guy, right? I sum 1 to n. So I have n fx over n. So it's just equal to expected. N expectation fx over n is just equal to expectation fx. So the mean of the left-hand side and the right-hand side is the same. So I said that I assume the mean to be, okay, let me, okay, I don't want to erase this, but at the same time, it's like, I shouldn't put it here, like, okay. Let me use some space here. So even though like when we don't have like zero mean, let's say I have variance of y here, assume it's not zero mean, but I can consider the zero mean version, right? It will be the same as variance of y minus expectation of y, because the variance will not change even you change the, if you change, I mean, add a constant or something, right? Like the variance is like, for example, I have a variance of a Gaussian distribution. So when I add a constant, I'm just shifting this distribution, right? The variance is about the shape of this distribution. It's not about the location there. So therefore, the variance does not change if I add a constant or subtract a constant. So I will have variance of y is still equal to variance of y minus this guy here, right? And no, I'm giving the solution now. Like you guys are finished. If since this guy is zero means, so it's a equal to expectation y minus ey square, right? So this is like the variance is equal to this guy. For zero mean, let's see. Okay, let's don't do this first. Let's still like assume like things are zero means. So if I have a variable is zero mean, then my variance of y is equal to the expectation of y squared here. So it's equal to this one square. Now it's equal to, I can expand that. I have like, first I can pull this n here. I pull n outside, I know that like there's a square here, right? So I have 1 over n squared get outside. So I have expectation sum over fxi and square here, right? And this will give me like 1 over n squared expectation. I can have the expectation go inside. So I have summation. I have two summation here now, right? Because I have a summation. I basically have two sum here and plotted together. I have some cost term and so on, right? So I will have like I equal to 1 to n, let's say, sorry, 1 to n, and then like j equal to 1 to n, fxi, f6j, right? And I can have the expectation get inside. So let me expectation fxi, fxj, like this. Now the thing like I need to use the assumption is like f is IID, xi is IID, so they are independent. Each of the I and j are independent. If I is not equal to j, they will be independent. And okay, this is like something, if you don't know, you should know. It's like if you have something is if they are independent, you have like fx, let's say, let me just make it simple. Let's say xy are independent, then I have expectation of xy is equal to expectation of x times expectation of y. And actually, you can get even this statement to be true for a weaker condition. when this whole is uncorrelated, actually, like x and y are uncorrelated. But like if you have things like independent, they will be uncorrelated, so you will have this whole. So therefore, like I will have this is equal to n square. So I can group the terms. Basically, I have some terms I equal to 1 to n that have like basically have I and j is equals, and I have sum over fxi square, right? And I have like the cost terms here. I is not equal to j, expectation fxi, expectation fxj here. But we know that like earlier we assumed that like x is like is zero mean, right? So we say like basically like we say like both y and x is zero mean to start with, right? So therefore like this will be equal to 0 here. So this will be equal to 0. So this cost term will be all gone. So then we will only have, let me erase this part here. So we only have this term left. So it will be just equal to 1 over n square sum over expectation xi square. And all of this I will have the same statistics, right? So I have n of this guy and expectation fx square. And note that like when 0 mean, this is also just equal to variance of fx, right? So therefore I have n variance of fx over n squared, so equal to variance of fx over n. And now let's go back to here. What I want to say here is that like, this is true, it doesn't matter whether you have 0 mean or not, because know that like for this left hand side and right hand side, they have the same mean here, right? So let's say if I subtract the mean, like as I said, like if I subtract the mean, the variance doesn't change, right? I start with y here, I subtract the mean of y here, the variance will be the same, right? But this one, I would say this is actually equal to variance of f equal to, okay, equal to 1 over n. How do I say that? From this will be equal to variance of this guy with 0 means, so it should be fx over n subtract the mean, right? Yeah, I think that's right. So, but of course, like this thing is just a constant here. Again, it won't affect the variance, so it's just equal to the variance of fx over n. So what I want to say is like, it doesn't matter whether it's like you have 0 mean or not. If you have some independent IID random variable, I mean, basically, like if you have some IID random variable, if you take the average of all these random variable, then the variance of the outcome of the average will be equal to the variance of the original variables over the number of elements there, over n there. So, okay, now I can go back to the proof here. So, okay, I guess if you guys don't have any question, I can erase this. So, I guess I will erase all this now. Again, like our objective is prove this weak LLR with this Chebyshev inequality, even though like I didn't show this yet. So I will show it later on. But let's say like this is true here. So I will take y is basically just equal to this guy, right? So then I will know the variance of y is just equal to, so therefore like the variance of y is just equal to variance of fx over n, right? So then like from the Chebyshev inequality, I basically will have probability of now y is this guy here minus the expectation of y here is actually just equal to expectation of fx. So I have this, and I will have like, let's say, I will set a equal to epsilon. So I have therefore 1 over mi and fxi minus this fx bigger than epsilon. Maybe I just bigger than equal to epsilon is less than equal to, now let's compare this side. So I have variance of y, as I said, is a variance of fx over n, and a, now a is actually epsilon, so I have like epsilon square. So we are done actually. Like this is a, as n goes to infinity, so this will go to 0, right? So therefore like we'll have this weak law of large number. And now let's go back to show this Chebyshev inequality quickly. So to show this Chebyshev inequality, we will use this Markov inequality. So the Markov inequality is like this. So I have like probability of some random variable x is bigger than equal to b will be less than equal to expectation of x over b. So that's some constraint for this x here. X has to be positive. So if x is positive, there's some random variable x, then the probability of x bigger than equal to b will be like bounded by this right hand side here. So the proof is very short actually. Like I can just I can just use the indicator function again. So I will say like indicator function is equal to something that if this argument is true, then I will have 1. If it's equal to 0, then if it is false, then it will be equal to 0. If argument is true and 0 otherwise. Then I can write x as follow. I can write x as like into 2 parts. I can write it as like indicator function x is bigger than equal to b, then I will say x. And then I plus indicator function x is less than b, then I will again multiply by x. So okay, it doesn't do anything, right? So I just split x into 2 parts. So anyway, like when x is equal to, so x is bigger than equal to b, then I will have this part is 1, this other part is equal to 0, then I will equal to x. Otherwise, I will have like this part is equal to 1, this part is equal to 0. It will still give me x. But then I write like this, then I can make a bound for that. So I can say like this is bigger than equal to just ix bigger than b times b, right? So because for this part, apparently x is bigger than equal to b, right? So I will have, when this is true, like of course I will have this guy is bigger than, I can add this again like times x. But of course both these two are bigger than equal to 0. I can also like say this is bigger than ix b times b. And then now if I take the expectation of both sides, so I have like expectation of x will be bigger than equal to expectation of ix bigger than equal to p times b here. So b is constant, I can put it out as like b expectation ix bigger than equal to b. This is just like the probability of like x bigger than equal to b, right? So then this gives me basically we are going to get this Markov's inequality. So is that Is that clear? So, oops, it's okay. I guess I don't need this anymore. So let's complete the entire proof by using the Markov inequality to show the Chebyshev inequality. Of Chebyshev equality using the Markov inequality. So so what we are going to do is that we can take let's say x in the Markov inequality. We take x is equal to y minus ey here. So just compare like this inequality with this inequality. So it takes like x equal to this guy. Actually, we want to take b is equal to a here. So and see what happens. So if we do that, let's see. Then I have the probability of y minus ey is bigger than equal to a. That is equal to, from this Markov inequality here. Okay, not yet. Let's not use this yet. And I can write this as okay, this probability is the same as y minus ey. The whole thing square is bigger than equal to a square, right? And now then I can apply the Markov inequality, and this guy is less than equal to expectation y minus ey square over a square. And of course, the expectation of this thing here, this is just equal to the variance, right? So therefore I have this is a variance of y over a squared. So this complete the proof of Chebyshev inequality. So and complete the, so therefore like we have together, like earlier we say like with the Chebyshev inequality we can show the weak law of large number, then we show the weak LLN. So I guess so any questions or like whatever? So the next thing I want to move on is I want to give a remark on the homework. Like, I don't know like how many of you look at the homework. Like, so let me, maybe. So in the homework, I guess I need to open that. Let me find my. I make up some random number, so I don't need to really look at exactly what number I use, but basically, if you let's see, I need to add your page maybe. Yeah. So in the homework, like if you didn't look at that before, like in the homework, basically say we try to estimate, do several estimation, like based on like whether like okay, maybe I should start with the setup again. Like we are in some tropical island that like the weather is like kind of consistent the entire year. So it's either go windy or sunny. And then if you're windy on one day, you can get like sunny on the other day or with some probability, or like you can get back windy yourself. Or like if you're sunny, you may go back to sunny and then you get windy. And then like based on your windy or sunny, then you have this different temperature. distribution basically. So this is a temperature distribution, and suddenly like you will have daylight have high temperature, and then like it asks you a number of questions like what's the probability that like, for example, if you have certain temperature higher than some temperature, what's the chance that like you are going to have like sunny weather, or like if today is like that cold, like what's the chance tomorrow is rainy, or like if today is rainy, what's the chance that tomorrow temperature is like higher than something. So this, if I guess like for the probability part, I think like you should have seen something similar before, so I don't worry about that. So you basically you just apply Bayes rule like a number of times, you should be able to solve that problem. So but I have the extra credit there. Like it's like if you're interested, you can work on the extra credit. It's like trying to do something like my Python code, like for the Monty Python problem, that trying to solve the same problem, like find those probabilities by writing a program. So in that case, again, like apparently I'm using the law of large number, but I'd like to give a remark or caveat here. Strictly speaking, like we have the model is a Markov there, because like the model in what we discussed in the Kelly criteria, and also like in the Monty Python problem, where we do like 10,000 times, 100 times, 1,000 times simulations, and each of these simulations are independent of one another, their IID. Now, if you want to do the simulation here, apparently if you are rainy today, it will affect whether tomorrow is rainy or sunny or not. And consequently, it will affect the corresponding temperature. For example, like if today is like rainy, the probability that tomorrow will be like colder will be higher than like today is sunny. So one is like something is practical. Is like in terms of sampling, you need to be careful. Like for example, in my let's see if maybe I want to share. Let's see, I look at this thing again. This aside. So note that like in my simulation there, like I do it like, for example, like I have the door, like in my original, in the Monty Python problem, like I can do things in parallel. Like each time I just like generate the entire sequence, like for like 10,000 simulations. But in the problems that we had, like I just mentioned, the tropical island problem, like I have to go like one day at a time, right? Because like they are all correlated one day with another. That's a I have a Markov chain there. And for second thing is like of course, like earlier, like we say, like we can do that because there's some theoretical basis. Like we have law of large number there, but be careful. Like in the law of large number, actually each of the random variable, like we say that sum of this I here, 1 to n, you converge to the expectation, and we have in the LLN there, we are assuming this random variable are kind of independent. So therefore, like, even though like you can do that, but it's not based on law of large number. The simulation, what you did, like for example, like if you do the extra credit trying to simulate that, you'll get the correct answer, but the theoretical basis is not by LLN alone, because actually that violates the assumption of LLN. So so I just want to be kind of like want you guys to aware of that, because, but I won't go into the technical part there, because that depends on this ergodicity. If you're interested, you can go to more math there. That is rather technical, even some very kind of like strict case or like special case like is very difficult to prove. Like so basically for the okay, the difference is again I will have the sequence. For example, if I think of the tropical island, I have weather here. Let's say my weather variables will be like whether it's sunny or windy. Like this can be like sunny or windy, sunny or windy, and then I have Q and all this. So all this will not be independent to one another, right? And I have my temperature, which depends on these random variables, right? TWI, let's say. I have this product of this guy here. What I'm saying, like now the problem is say all this W here is not independent to one another. So, and but it turns out it will still like converge to the expectation. Or in the sense like if I have the temperature, if I do this simulation, let's say 10,000 times or like sufficient amount of time, this guy will still like converge to the expectation of the temperature. That's the average temperature for the year. But that would be based on like something kind of like more kind of subtle than just the LLM. Would be like the ergodicity, like and so on. So, but okay, this is just a remark, but we won't go into detail for that. So, but okay, maybe like one more thing for about like the extra credit, if you guys want to tackle that. Just want to make sure, can you guys raise your hand or not? If for there, like I will have, for example, like if your day is sunny or rainy, you have a temperature distribution, right? I will have distribution, let's say. I will have some probability, let's say, I forgot, like, let me just make up something like 0.1 or like 0.2, or I don't know, it doesn't make this, maybe 0.3, let's say something like that. If I have something like that, maybe I have some probability, this 21 degrees, 22, 23. Okay, this is degrees Celsius, not Fahrenheit. So, and then like, of course, like given that like you are windy, let's say this, you have this distribution. It's not the same as like in the problem, but it's okay. I just randomly make it up here. So, do you know how to sample this? Like given I have a random variable with a discrete distribution, let's say in general, I have let's say T have a distribution, something like this, whatever, or actually I draw it a different way. So, and I need to sample some data from this T here. So I have T1, T2, T3. When I sample, meaning that like, for example, I sample like 100 times from the distribution. So hopefully I will have this, let's say this 0.4, I will have like 40 times approximately, we'll have this 24 degrees, right? So if I sample things correctly, of course here I ignore the change of weather, like from windy to sunny here, assuming every day is rainy here. So do you know how to sample this, like writing code to sample something like that? Okay, at least I have some. So I don't know how many of you are here. So if you don't know, like, okay, that's someone say no. Okay, maybe it's worth saying that even, okay, a couple of people say no. So, okay, this is quite common. So if you have something like this, like what you need to do, like, is like, you know, there's always a no matter you're using NumPy, MATLAB, or like C or anything. For example, NumPy, you probably have a random function that generally, I forgot like precisely, I think it's like NumPy.random.rand, probably just .rand, that will generate you a random number from 0 to 1. So what you can do is like, you can just let's see, what was that? Oh, okay, what was the last question? Okay, the question is basically saying that I need to sample a sequence of temperatures. So here I assume that every day is cold weather. So now I need to sample the temperatures. Maybe I need to get 100 samples here. And I have a distribution, it's like this. So I have like 0.1 probability to have like 21 degree, 0.2 probability of 22 degree, and 0.3 probability to have 23 degrees. Now I asked like, if you guys know like how to draw sample from distribution like that. Basically, it's drawing sample from a discrete distribution. So in general, like what you can do is, let's say if I have just maybe a K segment here. So I have P1, have like P1 here, P2 here, up to PK here. And then like basically I have probability P1 to get 1 and probability 2 to get P2 to get 2 and so on, have probability K, PK to get K. Now if I want to draw a sample from this distribution, what I can do is I can first like have this, or I will have a vector of probability, right? Let me call this vector, just maybe I call PS here. So it's like probabilities. So I have a PS is equal to P1 up to PK here. So now then I can do a Q sum for this guy to accumulate the sum. That's a function in MATLAB and NumPy also. Basically what it did is I will return something a sequence, maybe I call it CPS, maybe a Q sum of P. It's like P1 and then P1 plus P2 and then P1 plus P2 plus P3 and so on, then up to the last one will be the sum of all these probabilities, which is just equal to 1, right? Something like this. Now then if I draw a random variable, say uniformly from 0 to 1, so I can check, like, let's say I sample one of this, is I sample like, call it X here. I'll see like where X fall on this sample. So if on this like CPS here. So if X like fall somewhere like between like P1 and P1 plus P2, then actually it will fall between these two with probability P2, right? Because right? Because this sample X here is completely uniform, right? It can go everywhere uniformly. So with this Simon length here is just P2. So the difference between these two guys here is just equal to P2. The probability that falling into here is just P2, right? And then so if it fall in this guy, so I will just output 2, then it will make everyone happy, right? Basically. So similarly, if I have my sample X, I draw it again. If it's go beyond like this P1 plus P2 and P1 plus P2 plus P3, then I should just output 3. So basically, this in this case, output 3. And again, this will happen with probability P3, right? So that's exactly achieve what I want. So is that clear? So. Okay, yeah. So I guess that's a comment. If you guys want to try to do the extra credit, you will need something like this. So so that you can sample in sample discrete distribution. And okay, what next? Let me check. So that's the things okay, next thing, I think I went a little bit slower than I expected. I don't know like how far I can see. I have about like 5:50, right? So actually I still have about 25 minutes. Actually, I should have like quite a lot of time. So next thing I like to mention, like actually is like just a name that we already see that before, but maybe I emphasize that. So I just want to mention a term called discrete memoryless source. So and again, I want to go back to one of these original questions we had earlier about information theory. It's like we want to be able to quantify information. So to begin with, like we start with something like reasonably simple. So like we will try to quantify amount of information for this special case of discrete memoryless source. So I have, as the name suggests, discrete memoryless. It's just saying that the source will be discrete. So I have, say, like have some alphabet X here, and the number of the size of the alphabet would be finite. So for example, like you can output like my X can be like A, B, or C or something like that. X can be maybe like this. Maybe the alphabet is A, B, C here, and it's memoryless. So it means that like okay, I have this. I call this discrete memoryless source here. I'm going to sample this source repeatedly. And I'm going to output this X here. I get like each time a sample, I will get a something like from this source here. I can sample like n times S1, S2, and so on. And they are memoryless. So just meaning that they are independent. So this time I sample something should not depend on like what's output previously. So therefore, like if I sample like n times S1, X2, Xn, and this whole sequence here will be IID. Now the question here is like, okay, for this very restricted case here, well, no, I shouldn't say very, but a little bit restricted case here, what was the amount of information or like what should I say actually? Let me I can say like information generation rate. I don't know. This is a kind of a term I made up. So in the sense like if this just you think of this source like spit out some information here, how much information it actually spitting out per sample? Something like so as I said, like one way, like I guess last time we say like one very generic way to quantify the amount of information. Wow, you're quick. It is a good guess. Actually, this is a very good guess. But okay, this depends on your know that this depends on the distribution here. What you get the number, you're assuming that the distribution is uniform. How about if it's not uniform? So let's say if I have like PA, PB, and PC, they are not the same. They are not the same, it's not equal to 1/3. So how much information, I mean, this is spitting out from this like discrete memoryless source. More precisely, like you can think of that this way. For example, like if I draw a sequence of length n here, this is length n sequence here, then if I try to compress this sequence, I think of like the way I am, as I said, like how do we quantify the information will be like how much we can compress this information, or like what's the smallest space I can with the smallest space, what would be the smallest space we can kind of like still or like I should say, what's the smallest space needed to store this information without corrupting that? In the sense, if you compress so much, then if you recover that, there's no way you can recover. Basically, what you extract back will be just lossy, will be lost. There will be loss, basically. So this, the way this is a very nice way is you can see is we can use the law of large number. Surprisingly, we can use the law of large number argument to solve this problem. So what we are going to do is say, let's see, I have a sequence like this way, x1, x2, xn, and so on. And they have a distribution like for this, let's say the probability distribution here is just P here. Now let me consider, of course, x1, x2, each time you draw is a random number. You can, I need to let's just be a number, but a random variable. So P itself is a probability distribution, but it's also a function, right? Px is actually a random variable, right? Px itself is a random variable. If x is a random variable, Px is a random variable, right? Now, if I consider, let's say, I draw a sequence like of length n, also I have the sequence eventually is x1 up to xn here. Actually, I should also mention a shorthand notation is very common. Sometimes I refer this as a x1n, something like that. So it's like not x1 to the power n, but it's like from x1 to xn. This is like common in like information and literature, or like some other discipline, or like sometimes people also write like xn, simply xn to that will be the same as like x1 up to xn. Now, so what was the probability for this guy? Because we assume that this source is discrete memoryless, right? So this sequence should be IID, so each of them should be independent. So this should be just equal to px1, px2, and so on up to pxn, right? So I can write it in a Porter form. Is I Porter pxi here, I equal to 1 to n, right? Now, if I take a log for that, so it will become a sum, right? So I have log of this guy. I will have this. I shouldn't write a equal sign, but I start with something like that. Okay, let's say I have log px n, that the joint probability here will be equal to log sum of this log pxi, right? And note that like here, I still writing the capital variable here. I'm not talking about realization. It's that you can think of each time I draw a sequence of length n here. So each time I have a different variable. Each time I have a different realization. I have a random number here. But know that these terms actually will converge, right? Because I have this guy here, like each of these log pxi now, actually a random variable itself, right? It's a random variable. Also, this random variable are independent and identically distributed. So because each of that is a px, and so therefore, like it will be just what? This will actually converge to expectation log px almost surely, right? So this is by law of large number. And by the way, like typically because like p is less than 1, right? So and people like something is positive, so therefore like we like to put a negative sign here. So I put a negative sign here also. So I will consider this instead. And now what? What we have is actually, I have this guy. Note that like I draw a sequence. Actually, let's reflect a little bit again. This is a very simple like algebraized, but the consequence is actually pretty subtle. We are drawing a sequence here, random sequence here. What I'm saying that like each time we draw the sequence actually have the same probability, because like the log of that probability will always converge to a constant, right? As long as the sequence is sufficiently large. And what's the probability then? Well, I can just rearrange the term, right? By the way, I will just rename this, I call this H here. I'm actually more precise, I call it this HX here. Or let maybe just H first, like call it H here. Then I will have like PXN actually will converge to, actually, it's good not to use log, lateral log. Let's use log 2 here, just make the unit nice. I don't write log 2 here, but like you understand it's a log base 2. So then I will have like this will converge to 2 to the minus, wait a sec. Oh, okay, I'm sorry, I'm missing something here. This, how do I write it? Yeah, I should. I should write like this, because that one was not average, that was a sum, right? So this guy will converge to minus log P instead, right? Because I'm basically, I have take an average of this guy, and each of them are ID. If I take the average of all these, then we just converge to the expectation of this one here. So again, I call this as H. So therefore, like if I rearrange the term here, Px will be just equal to 2 to the nh, right? To the minus nh. So I have a minus sign here. So is that clear? And again, like this is kind of interesting, because you have this memory, this source here. And what I'm saying, like if you draw a sequence sufficiently long, then for each of the sequence you pull out from this source, actually will have the same probability. And this probability is just given by this 2 to the minus nh. Maybe I put back this x here. And actually this guy, we call this the entropy of the source. Source x here. So, and it's defined by this guy, this hx is equal to expectation minus log px here. And now actually I'm ready to answer the question, like what's the amount of information for this source here. Note that like if I draw a sequence, like a long sequence here, each of them actually have the same probability. And each of them with probability is equal to this guy 2 to the minus nhx here. Then note that like that's exactly the case some of you guys answered earlier. If I have something that's uniform, let's say if I have I have I have a dice, like a dice and I have an outcome, like have 6 different outcomes. If I ask you like how many information are there like for the outcome of a dice, I guess many of you will answer this is equal to log 2 over 6 because I need not 2 over 6 so many bits to store this 6 outcome, right? And this 6 outcome is actually uniformly distributed. Right? Each of them is equal to 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Yes, let's see. So yeah, so now if I have actually, this is actually exactly the same scenario of this one here. If I draw this sequence of length n here, each of them will be uniformly distributed because each of them will have the same probability, the same probability p here, and so since each of them have probability p, and the total probability will be 1, you can think of that would be approximately 1 over p so many different items here, right? And the number of bits will be needed to store so many items will be equal to log 2 1 over. I shouldn't reuse this p here. Maybe I instead of like I write p here, let me call this q here. So each of these have q. So q is the probability of like of drawing each of the sequence here of length n. So you draw a sequence of this length n here, you get a sequence. Each of them will have probability equal to q, and they're all the same. So since they are all the same, so approximately how many of these sequences will be there will be like 1 over q, right? 1 over q, so many of them. And how many bits I need to store these sequences will be just the number of these sequences here, like take the log 2 of number of these sequences, so many bits, right? So it's equal to log 2, log 2 1 over q bits, right? And again, like what is q again? Q is equal to 2 to the minus n matrix. So therefore, like let me use space here. So therefore, I have log 2 1 over q will be equal to log 2 q is equal to 1 over 2 to the minus nh x, right? And this is equal to nhx, right? Or like maybe I write one more step. So log 2 nhx is equal to nhx, right? So log, and because it's log base 2 and 2 to the power just cancel one another. So we get nhx back. So we are already here. So therefore, like if we have a sequence of length n, we actually need nhx bits to store that. So therefore, I can say the information content per sample of this discrete memoryless source will be just nhx over n, right? Will be just equal to hx. And therefore, like for a discrete memoryless source, you can think of the information content, like, or actually the entropy of that source is just equal to hx. And where the hx is just equal to this expectation minus log px. And that's a kind of funny story about the history of entropy. Sharon discussed this thing like with von Neumann before, and von Neumann just, initially he told von Neumann, like, von Neumann asked him like, what do you want to call this thing? He said like, he was thinking like something information measure, information content or something like that. But then like, von Neumann just said that like, well, why don't you just use entropy? Like, because like physics have something similar, like in statistical physics. It's not exactly the same, but like it's already calling that entropy. And if you use entropy, like, of course, one thing is because someone else already have a very similar idea, you should use the same terminology for that one. And another reason, like from Neumann's side, is like because at that time, like no one know what entropy is exactly. So he said that whenever you're in a debate, you just say like this is entropy, then people will just shut up. So therefore, like Shannon just like follow his like kind of advice and call this thing entropy. So maybe let me pause a little bit, like just give a couple examples, like give maybe a concrete something. So, but remember, like we kind of have and by the way, like I forgot to mention, like there's some terminology or like buzzword for that. Like you may not need to use that, but like it's good to know like what they mean. Like when people say that and forward to you, there's something people call like how to spell that? Totic equipartition. So it's just referring to the fact of this thing. So if you sample from a discrete magnitude source, sample a long sequence, then each of the sequence will have the same probability. So you can think of it like you have the probability space is partitioned into these tiny pieces. Each of these pieces will correspond to the probability of like getting one sequence. And that sequence will all have equal probability. Therefore, people call it asymptotic equipartition. And equipartition is obvious because it's equally partitioned the probability space. Asymptotic is just meaning that you are taking n to infinity, basically. So maybe just give one simple example, like a flipping coin, let's say we flip coins, right? So let's say X will be just have an alphabet like head and tail here. So then I can have like the probability of head, right? Is equal to maybe P, something like that. So remember that the entropy, H. Okay, another one thing that I remark here is that, of course, I rewrite the entropy. This is a convention everyone use, like the entropy of that random variable. But of course, when you write this, you know that like it actually not depends on the random variable, but depends on the distribution of that random variable. So this is actually equal to the expectation minus log px, right? Something like that. And how do I write this? So and this will be equal to probability x is equal to head. Okay, when probability x equal to head, what's this value here? It will be like minus log 2 what? So when x is equal to head, this will be px is equal to p, right? So this is minus log 2p, right? And then I plus probability x is equal to tail minus log 2 1 minus p here. So therefore equal to, of course, this is just p here, right? P minus log p. I'm skipping the 2 here. Now it's like 2. And probability x is equal to tail is 1 minus p log 1 minus p. And when p is equal to 0.5, you can verify very easily. So when it's 0.5, then this guy is equal to 1. Wait, this guy is equal to 2, right? So let's see. when P is equal to 0.5, I have equal to minus 0.5 log 0.5. This is equal to minus 2 here, minus 0.5 log, again, like 0.5. This is also minus 2 here. So that gives you, sorry, this is minus, sorry, this is equal to minus 1 here. Log 0.5 is minus 1, yeah. So therefore it gives me like just equal to 1. So this is 1 bit, just as people will be expecting. So if you say have a biased coin, no, unbiased coin, you flip it, the amount of information is just 1 bit. Okay, so I guess I will just stop here, like it, and we'll come back next Wednesday. And yeah, so if you have any question, like just email me or something. Yeah. So if you guys have any question, comments, or not, I will. Or if you have something you want to ask.
So I have a
I'll
question.
stay a couple minutes, but yeah.
So what's the, so you are saying the unit of entropy is bit, right?
Yes, actually, that's I didn't emphasize here, but it depends on what kind of log I'm using. It's easier. Okay, it's very common now. Like everyone will just use log2. If you use log2, the unit will be bit.
Okay.
Yeah.
Okay. Thank you.
So we can. Yeah.
Yeah. One thing, Dr. Samuel, I wanted to know that
yes.
Where can we find these lectures if we want to revisit them? These recorded lectures that you have.
Oh, okay. Say that again. Like you said, you cannot find a recorded lecture, or like.
No, these recorded lectures.
Yes.
So how can we find them on Canvas or somehow?
Oh, okay. Yes. Do you see my website? So, let me just share the screen again. Let's see. Share my. Let's see. If you go to Canvas, it should have a link to my personal website that with the I'm here. Like you should have found the video. Yeah. So I will also put it up today, but it will probably take a while because like yeah, it takes some time to convert or something.
Okay, thanks.
Yeah. So anyone else have any questions? If not, I'm shutting down. So hearing none, so I'm shutting down the.
See you next time.
Okay, see you guys.
Yeah, have a nice weekend.
Oh, you too. It's early, but yeah.
Yeah.
Every day is weekend. Yeah. Okay, see you guys.
Yeah.